record this here, and this will be posted. Still working out. LMS has been proving to be, or at least the media site has been proving to be a bit flaky with regards to uploads and things, but we'll, in the process of getting that worked out. Semester is still early. That's my story. I'm sticking with it. So we're going to sort of hope that some of these bumps in the road will be taken care of. So let me look around, make sure. Okay, I see volume over there. That's good. We seem to be streaming. We seem to be recording. We seem to be live on Discord. We've got 2, 4, 6, 8, 9, 10 of us, including myself. And that will have to do, I guess. So, if you have seen, or if you haven't yet, I just posted a link over on Discord. Speaking of Discord, make sure, double check that you have signed up for one of the slots that is in the actual class time. I think last time I checked it was pretty close. I think there might have been one person who hadn't. So it looks like we're pretty good. Most of you just went ahead and decided for the slots in class, and it looks pretty full. So I think it's going to make sense to kind of do it that way. We'll see. There may be weeks where we say, okay, we're going to have some lecture that's going to take a little extra long one day, and maybe we wind up bumping things. So that I have to figure out exactly how I want to do that. If we just bump everybody, so everybody kind of slides back by a week, or something like that, or we skip 1 week and then we get back to it. I don't know. We'll get there. Playing it by ear. So hopefully everyone had a good weekend, and let's see, I did have a bunch of questions that got answered or asked and answered about kind of the latest things, which is great. So I assume people are sort of now settled in, and that everyone has, and if you don't yet, even if today is not your day, so today as far as check-ins go, I have, and I'm just gonna pronounce your RCS IDs as best I can, because that's what I have. Pizia, Sidjwa, Lins9, Frums, and Stolpe. So those are the folks I have for today. So 5 for today. That'll start basically the last 50 minutes of class. We'll see how long they go. I'd imagine this week is pretty much a light check-in. What I'm going to want, hopefully, when it comes time to check in, you're going to basically, hopefully, the plan is share your screen, kind of walk me through some of the programs that you've done from the book, at least one example that you've sort of done from the homework, and, at this point, you should also have sort of a project, and the project is really just something that wasn't directly in the book. Could have been, certainly inspired by the book and so on, but it's really just so I can kind of get a feeling for, your coding style, where you're at, is it all running? So it's the first one here. The first project is definitely a soft launch. The first homeworks are soft. We'll be getting more intense as we go, more into things as we go. The first 2 chapters, actually the first 4 chapters, I'll say, the first 4 chapters of the book are really, really, really the foundational pieces as far as OpenGL goes. So by the time we get through chapter 4, you'll, kind of had what 80% of people think is all of OpenGL, or something like that. By the time you're done there, you're hopefully, you should understand vertex buffers, vertex shaders, fragment shaders, the basic operations of vertex attributes and their buffers. We're going to do some texturing. We're going to understand what interpolation is and how the various pieces in between the pipeline go. And so a lot of the basics are going to be, hopefully in hand by the time we're done with the first 4. And you're also going to have, hopefully by the end of today, a little bit of a better idea with regards to some of the 3D math I'm going to be using kind of over and over and over again, and why it's important. So I'm buying a little bit of time for our late arrivals, and hopefully I'm just going to jump right back into things. So let's see if I can do this. I got to go over to OBS and transition back over here. Okay. Any questions on any of those things? I got to do my best to kind of keep a track of time, because obviously with the check-ins, I'm going to need to be on time, or pretty good on time with that. They start at basically 1:10. So in half an hour, 45 minutes from now. Yes, you should have done, so with regards to everything, the idea is that keeping up is basically following the steps in the book. Like I said, this is largely sort of a lab structured course. So you should have, examples done up through. A lot of the sample code is actually available on the CD of the book. So you have access to a lot of the sample code as well. So that's that. But you should also do at least one or two of the examples or the exercises at the end of the chapter as well. Okay, so be prepared kind of to convince me, basically. Convince me that you've been following along, that you've done the work, you've typed things in, you've gotten them to run, you've sort of understood what we've been talking about. Okay, and we'll get more and more concrete as that goes. All right. So we've been talking a lot about triangles, and what I realized is I had a sort of an argument with myself at one point saying, I was looking at some other things and they're referring to triangles as tries instead of triangles. And, that seemed, kind of interesting. Or why would we say tries instead of triangles or triples instead of triangles? And it actually is a very good point. And this does bring up something that was sort of discussed last week, in that we are talking about generally triplets of vertices. Right, so we have three vertices that normally are making up a triangle in the naive sense. Right, we have the 3 points, and then we have the containing portion of a plane that is represented as being sort of in between those, and that's what's telling us what basically a triangle is. Sounds a lot like what we would normally think of as being a triangle. But then the question came up, sort of about I mentioned, maybe you have normals at each edge of the triangle, and that sounded odd because normally a flat triangle would just have a normal that pointed out from the center of that triangle. That make perfect sense to absolutely have that. So I was saying, well, what if it wasn't a flat triangle? And that is a bit confusing. That sounds, aren't triangles flat? Are they smooth surfaces? Are they, they something more than just a triangle? So I am liking this term tri or triple more and more, and maybe we'll probably slip up a few times and refer to them just as triangles, because largely, again, the foundation, we think of them as triangles, but they are really triples of vertices. And in the normal case, those triple vertices do define a triangle. That's the naive case. We can always do that. And early computer graphics hardware, that's all there was: flat shaded triangles. And, well, let's leave the quads apart. But early iterations on our hardware, flat shaded triangles. But now, if we think of them as triples, we can say, well, okay, really what they are is they're points in space. A vertex normally has a point in space. It has a X, Y, and Z location, usually. And then it has other information for that point in space as well. Right? It could be a UV coordinate, it could be a color, it could be a normal, it could be any number of different things. Okay, and then as you put together collections of those vertices in space with all of their attributes, they're going to form geometry. Right, that simple vertex on its own is just a point. It's not a shape. It has no, geometry really, other than it's just a point. So if we put groups of them together, they are going to form geometry. They're going to form meshes potentially. They're going to do all sorts of fun things like that. So I wanted to introduce, and here's just sort of think of this. This is not a hard, fast thing that I want you to, maybe someone will take from this a bit of inspiration, and hopefully my computer doesn't crash now. I saw my fan just kicked up a little bit. And this is a fun piece of geometry. It's called a Rollo tetrahedron. Okay, and it looks an awful lot like a pyramid, except it has curved sides. And it's actually made up of a set of spheres, that each of the spheres is centered at the vertex of centered at the vertices of a regular tetrahedron with length size s. Okay, but the result is clearly not a flat thing. And even though it's defined ultimately by those vertices of the tetrahedron and, some parameter s length from there. Okay, so we can do things like define objects that aren't necessarily flat. Okay, we're going to use those vertices to establish the geometry, but what we ultimately do with those can lead to things that aren't just flat triangles, even though the most basic form that we have in computer graphics usually is a flat triangle. Okay, so if you look at this, tumbling Rolo tetrahedron here, you can imagine that all of these surfaces are not smooth. Or they are smooth. They're not flat, though. Okay, there's some math involved, but ultimately, the parameters that we have to provide to define that are largely, in this case, it's just the vertices and then some length. So you can imagine what we could do if we even had more information about each vertex. Right? So I'm going to go ahead and close that. If now the Rolo tetrahedron, maybe some of you might be inspired by that, future project. Maybe you want to look into the Rolo tetrahedrons and things and see how could you implement that? Could you draw a Rolo tetrahedron using a shader? That's a future thing. Any questions? Hopefully that sort of inspires the thought about what can we do with these primitives that are beyond the obvious, right? And as time goes on, as hardware gets better and better, and GPU cycles get more and more prolific, we do more with these things. Okay, so let's talk about triangles just a little bit, and then I want to wrap up triangles as a concept, more or less, and then get back to the math, kind of hopefully wrap that up today. So we have our triangles, we have a winding order. Normally the triangle that's described by a set of vertices is planar. Certainly the vertexes are going to be coplanar, right? But that doesn't necessarily mean that what we're going to describe ultimately is going to necessarily be planar, right? The vertices themselves, they are coplanar. Does that make sense? Right? They all lie in the same plane, but what we do with them after that, whether we curve them or depth map them and so on, we can sort of violate that coplanarity if we want. All right. So basic things, we can calculate a normal for a triangle and so on and so on. Now we talked a lot about the vertex format and the things like the position, potentially a UV coordinate, potentially a normal, and so on. So we're going to go quickly over those. And we'll hopefully get that quiet. Somebody's dropping something off. So, one other thing worth mentioning. Now, sometimes we are telling the OpenGL drivers that, yes, we are working with triangles. We're actually using triplets of vertices, but we refer to them as triangles. And often we go kind of beyond that. You'll see things where we start to refer to triangle strips or meshes or points and so many things beyond just a set of triangles. So sometimes it's not, we are using these collections of vertices in slightly different ways, right? Because if we think about collections of triangles, larger meshes, first off, the naive approach to specifying some collection of them would be to say, okay, for every triangle in my mesh or every triangle in my collection, for every vertex, I'm going to specify a vertex for each corner of the triangle, for every one of them. So if I have 6 triangles, I'm going to have 6 times 3 vertices that we're going to deal with, right? But that is unnecessarily repetitive, memory intensive, redundant, and so on, right? Because if you think about it, if we do have a mesh, like if you look at the left-hand side of this slide here, that what's really happening is that there is a shared vertex at the center of our collection here, our mesh, right? Now, the nice thing is if they do actually share things, now you'll see that's shared, but then that's shared among all the triangles. And then each edge vertex is shared between 2 other triangles. Well, between 2 triangles here, right? So we have lots and lots of shared vertices. In fact, we have 1, 2, 3, 4, 5, 6, 7. We only have 7 vertices, despite the fact that we have 6 triangles, which naively we would think had 18 vertices. Right? We actually only have 7 that we're sharing among these triangles. Right? So there are ways to work with indexed vertices. We can refer to these vertices multiple times by an index as opposed to specifying them over and over and over again independently. Right? So we're going to start to see examples of code in the book that talk about that. And it's nice because they will be absolutely shared. So the nice thing is if you have shared vertices that define a shared edge, there's no gap in between. There's no issue with math trying to accidentally or because of rounding error and so on, things not lining up perfectly. Okay, so that's something that's really nice about using indexed approaches to vertices potentially. All right. So this is this concept that we have an indexed triangle list. So in a triangle list, we could store each vertex once, and then we specify our triangles by supplying the 3 indices for that particular triangle, right? So 0 might be the vertex that's shared among all my triangles. And then I can say, okay, which 2 other vertices go along with that triangle? So in this example, 0, 1, 2 is this top triangle here. 0, 2, 3 is the one to its left. 0, 3, 4, and so on, working around clockwise. Right? So instead of specifying the actual vertex, the actual set of 3 vertices for each triangle, we're going to create an indexed list or an indexed array of indices to specify our geometry, to specify which vertices we're using. And that's much more memory efficient because we're not repeating things over and over and over again. Right? Now, we also have a way of specifying strips of triangles. So as we're building up geometry, again, we don't have to do it necessarily kind of, just draw a single polygon or single triangle at a time. We can say, okay, here's a structure that is made up a set of triangles. So the triangle strip is even more efficient. So it's similar to an index triangle list, but after the first 3, each subsequent vertex or index forms a triangle with the 2 previous. So what does that mean? Okay, we have, say, okay, the first triangle is 0, 1, 2. The second one would be assumed to be 1, 2, 3. So all we have to do is specify the one new vertex there. So if we had this list, 0, 1, 2, 3, 4, 5, 6, 7, we would follow it through. We'd say 0, 1, 2, that makes the first triangle. And then we add vertex 3, which now we have 1, 2, 3, with the next triangle. Then we add 4, so we have 2, 3, 4, which is the next triangle. And then we add 5, we get 3, 4, 5, and so on. Right? So an even more efficient way to use triangles to build up more complex geometry. So pretty powerful primitives here. And ultimately, yeah, they're this odd land in between. For now, if we think of them in their purest, simplest form, they are just triangles. But we are going to be, from those triangles, we can build more complex meshes. And if we do provide enough math and enough, know-how behind them, we can do things that aren't necessarily even flat. Right? You'll start to hear terms later on about things like B-splines and patches and Bezier curves, and all that sort of thing. That's going to allow us to specify geometry based on control points or given vertices. Think about our Rollo tetrahedron again. Specify a certain number of vertices and one additional parameter, boom, we get this really kind of cool, smooth shape that certainly looks more complex than a flat triangle, certainly. But because we can express it in terms of a geometrical formula, we can specify it with far fewer parameters than if we had to actually draw lots and lots of triangles to create that in a smooth way. All right. So let's see. We don't really need to talk about so many of these, so on. This is more, general OpenGL. You've seen the draw call and so on. We're going to see that. So I'm going to jump from there. We've talked, it's sort of enough for today about triangles or tris and vertices and why they're kind of important like that, to think of them that way. And let's go back over to the math side for a bit, right? So again, we'll get to sort of some fundamental concepts that once we have them, a lot of OpenGL and and graphics are sort of going to unfurl, hopefully for us, right? So last time we started talking about matrix transformations or matrix transforms, and we went through some of the basic ones. We started off at least with the translation matrix, where all we want to do is say, take a point and do some sort of operation, and it's going to be a matrix multiplication that's going to slide it somewhere in space. It's going to offset it according to an x and a y and a z. So we're just adding an arbitrary offset to a point, right? To a vertex. We use the translation matrix to that, which had basically our translation, our tx, ty, tz. Those are the important parts there that are going to cause they get multiplied by 1, which is our homogeneous parameter there. So that's going to give us that pure translation. And here's how our GL math library, that's where we can create a translation matrix, and then we multiply our vec4, which is our point, times our translation matrix, and we can translate the point around. We do scaling by applying a multiplication to each of the existing components, the x, the y, the z, and that's going to basically push us further along that axis or pull us towards the origin according to that each of those dimensions, right? So it's just a pure scaling of that particular parameter. If we want to do a uniform scaling, all those s's have to be the same. So if we want to shrink an object towards the origin, that's how we would do that. Or shrink a set of them. You can imagine that might be a little bit trickier, because if you're shrinking a set that's not centered around the origin, that's kind of interesting, right? Let's start. Does everyone kind of get that idea? Right? If I have a uniform scale and they're at the center of the object is the origin, all of them are going to collapse towards the origin, so they're all going to shrink or expand appropriately. But how often are all the objects in the world centered at the origin? Right? That's where it gets tricky, and we'll start to see in a moment how we're going to deal with that sort of thing. That things aren't always at the origin. But our kind of naive translation is going to push things around, and then our scale, well, we can scale things so we can get hopefully beyond that. And then we talked a little bit about rotation, and rotation is tricky because the problem is, in order to rotate on x, we are relying on y and z and using cosine. To do y, we're relying on x and z, we're relying on x and y. And there's an order, and we have to sort of do these things in a certain order to get them in a matrix. We can do them. What we're basically talking about here is Euler angles, right? We have an x rotation, a y rotation, and a z rotation. And we have these matrices that we can apply the appropriate, was kind of a sort of a combination of scaling in multiple dimensions that kind of moves us correctly. And for now, you can kind of think of that way in a lot of naive systems, and basically until relatively recently, mathematically that is, we could rely on them when we're using computers, and so some issues came along. Not all the concepts. We're going to talk a little bit about these odd things called quaternions. But thankfully, we can kind of go back and forth between kind of this simple, what seems to be a simple thing, x, y, and z rotation, and this kind of abstract thing, a quaternion rotation. So, but for now, you can think of rotations. You could do them. You can do these sort of rotations with another transformation matrix, right? You just plug in the right values here to rotate by x. You plug that in, and then you can multiply that times this y rotation to get rotation across both, and you can multiply that times the z rotation to get that, and that's quite often will work. There are some interesting cases where it doesn't work. All right. So this is in our GL and our GL math library. Normally we're going to have a rotate, and we're going to basically specify what that angle is. Now you'll notice here, we create this rotation matrix, and we multiply that times our vector 4. So you'll notice here in the mid-1700s, a mathematician Leonhard Euler, that's Euler, that's how I was pronounced it, showed that a rotation around any desired axis can be or could be specified instead as a combination of rotations around x, y, and z axis. So it is a combination of these, and it's been come to known as the Euler angles or Euler rotation. we're using Euler angles to do simple rotations here. And that works most of the time. Let's see how much time we have today to kind of get through this, and we can talk about when it doesn't work. So let's talk about vectors, core concepts, right? What a vector is, often a vector seems to be sort of used interchangeably with this kind of point in space. But when we're talking about a vector as just, an x and a y and a z, what differentiates it from a point in space? Well, we assume that it is actually pointing from the origin to that location in space. That is the vector that we're really talking about there. Not just the location, but it is that location with regards to the vector that's formed between the origin and origin and that location, right? So if we don't, right, you can imagine we can move vectors or add vectors together by assuming that a vector starts at some other location, right? And that's what's happening as we start adding vectors together, or subtracting vectors from one another. So for example, here the vector v is basically the translation between 2 points, right? So you can have a vector v, in this case p2 minus p1. The vector itself would be the subtraction of those, and that would be the same thing as, you see this v here, the same thing as that offset from the origin, right? So the vector on its own is really only representing a position based on the assumption that, where did that vector originate, right? So that's why we see this p3 here is p2 minus p1, gives us this location here, and it's the same. Now, if you notice, if you actually started here and you subtracted off these values, it would get you there, right? So it's kind of a simple translation, basically. So vectors are your friend. Often we think of them as kind of sets of numbers. So you can kind of think of this vector as being, it's a triplet. So it is. Let me make sure every so often I'm worried about my computer crashing. Hasn't crashed yet. But also this vector, vectors in computer science, sometimes we think of them as arrays of numbers. We have a set, a collection. So here we do have that notion of, there it's a three-dimensional thing as well. But we're really talking about this kind of structure that has, direction and a magnitude, sort of really what's going on, right? A vector sort of points to some place. It has a direction, and it has a magnitude to how far you go in that, right? So x, y, and z, we can actually say, okay, this points at a certain direction. It points at x, y, and z, and there's a certain length to it, right? So vectors are your friend that way. Once we have vectors, we can start to do certain operations with those vectors. Now, you can imagine the edges of our triangles, they are just vertices, so we can subtract the two, and we get vectors in between the different vertices that we can work with to various things, right? Now, the first one, and hopefully everyone has heard of, I assume, since we did talk about, previous math. Let's take a quick poll over there. With dot and oops, let's see if I have to get my poll correctly here. I don't have an iClicker, so how are we with dot products and cross products in general? All right, pretty good. Ooh, lots of good numbers. All right, so we'll be fairly quick. So the math behind them is pretty simple, right? So I won't get into that part. So let's talk about potentially the applications, which is going to really be the important part here. And the nice thing about, I can kind of skip over the math real quick because, well, a lot of the libraries actually would do the math for you anyway, to tell you the truth. So if you do feel uncomfortable with dot product and scalar and cross product, we'll leave that for another day. Okay. So interesting thing about the dot product, if we take the dot product of two vectors, the dot product is a scalar product. It does wind up, we wind up with a single number from the result, even though we have, more than more than one dimension, we wind up with this one-dimensional scalar. And from that scalar, though, we can tell a lot about the relationship between two vectors. We take the dot product between the two, we wind up with a scalar that tells us, for one thing, we can figure out the angle between them, right? And that's really the main thing that tells us. It tells us the angle between them. But from that angle, we can do lots of things when it comes to about, the geometry of the directions that they're pointing in. Not only what the angle is, but are they sort of, what does that number tell us with regards to how similar they are, or how much would one kind of project onto the other? Because you can say, okay, the more aligned they are, the closer they are to being, the smaller the angle is. If you project the two onto one another, they're going to contribute quite a bit. If they point in opposite directions, they may cancel out with regards to a certain component. All right, so we can use that to sort of figure out, okay, how do they potentially are they lying in the same general direction, or if we needed to project one onto the other, in terms of physics, perhaps we have some sort of force that we're trying to add to another force, we could use that sort of thing on, right? So dot products are useful for that kind of relationship, that kind of spatial relationship between vectors like that. And the other of the famous group here is, of course, the cross product. Okay, now the cross product is not a scalar. We wind up, we take the cross product of two vectors, we wind up with another vector, and, according to the order that we do these in, we will wind up with, if we cross two vectors together, we wind up with another vector that is basically perpendicular to both of those. Okay, that's the important part. So we get a vector that's perpendicular to both of those, which basically means we have the normal between those two. All right, so if we have, assuming V is ABC and W is DEF, and we use, we basically are subtracting the two, we wind up with this R, which is perpendicular to both vectors, and that becomes our normal, right? So if we had that flat surface, that would be that normal vector that points straight off that. So we can say, okay, at that corner, if it was flat, that's the normal. Very, very, very important. Okay? So we have a way to get the angle between vectors and the normal that is perpendicular to both vectors. Pretty basic, but pretty powerful. All right? So cross product is useful for finding outward normal vectors. And I say outward because, of course, we have some winding order and things. We can make some assumptions and kind of figure out what's going on. And we, as long as we have those assumptions in place, we're great. We know what direction things are facing in, right? So here we are. We create some other geometry and we say, okay, we have these two vectors. We can create a normal. We know that's on the outside of our geometry because of the standards and practices we have in place, right? Whew. All right. Now, buckle up. I mentioned before about this notion, we started talking about scaling and translating and so on, and this kind of weird thing like, okay, as you scale an object, for example, the assumption is, just in a naive case, you would, if you just scaled, you need it to be centered around the origin so that it would scale appropriately, because you didn't want, things to be shifting in odd ways, right? So to scale something at an arbitrary location in space, you might start using kind of combinations of transformation matrices to kind of create, one larger matrix. And it gets, as we start using these in 3D graphics engines and to kind of represent models and multiple things, how they interact in space, we have to sort of deal with this notion of, multiple transformation matrices and how they all work together. And there are three very, very important matrices transformations that you're going to see over and over again that are important to understand why we have the three of those. They're the trifecta of, kind of working in OpenGL or any sort of transformation-based representation, a scene sort of thing. Okay, so imagine you have a model, right? We have a set of vertices that form a mesh, that form a model, and they all have, they're located in space according to however we modeled the program. We assumed some zero in the world, and we just kind of built them around, and there they are. They were built as a model without really regard to where they would be in the game or in our scene, right? We just kind of created that model. The model doesn't really know where it is in the scene. It's just the model. Every vertex has a relationship between some arbitrary origin. Okay, so that's known. Their initial geometry is known as their local space or their model space, right? That is the space in which the model is defined, usually centered at the origin. Why? Because that's convenient. If we want to translate a certain point, we want to scale the whole model, we have a common origin to refer to. It's convenient, and the model just knows about the model. Okay. Now from there, if we then said, okay, well, now I want to put that model into a scene, and perhaps I put multiple versions of that model even into the scene. Now, each one of those models may occupy a different space in the scene, and it may even have some sort of different orientation in the scene. So each of those models might need to have some location as far as world space. They have some location in the world, some orientation in the world, right? So if we look at this slide, the world space, the dimensions and orientation of the simulated scene being built, right? We have this world space that we're working in, and each of the models within there, the matrix transformations that are concatenated together that place an object in the world space is ultimately called the model matrix. So for that model matrix, once it's not the origin anymore, once it's not 0, 0, that becomes its location in space and its orientation in space. Right, so we go beyond that simple model, that naive model orientation about the origin, and we can now kind of move it somewhere in space, and now it has the model matrix that defines it for that. So each model will have a model matrix. Okay? So what else do we have? What other matrices or transformations do we need? Now, everything has its space, its point in space. And then ultimately, in order to be able to render anything, we have to have what? We have to have, if you're looking at the slides, you'll probably say, well, we need to have a camera or an eye, some viewpoint, something that is looking into the scene, right? That's going to figure out, okay, are we looking at the back of these things? Are we looking at the front of these things? Where we are in space? So for that, we have a camera, another object in our world, which needs to have its orientation, its position, its transformation. Okay, that would, if you look just at that transformation, that'll tell you where the camera is in space. Okay, so the world space is as seen from a simulated camera or eye in this case. You imagine here we have the objects in the world space. Don't worry about the projection plane necessarily yet, but you can imagine, okay, now we have these objects and we have the eye looking at them. Okay, so there's a relationship between the two. Let me look at, make sure I get this. It may come back to a concept if I don't cover it satisfactorily in the next 10 minutes. Okay, so we have another transformation that establishes where we're looking at or how we're looking at that. Now, you can imagine if we're looking down towards something, it's the same as changing the orientation of that other object to look in the opposite direction. Right? That camera looks down, it's basically having the object that those are looking at are sort of looking away. So there is a relationship between the camera's transform and a perceived version of the object's transform. So there are ways we can kind of get these to work together. All right. Oops. All right, so in OpenGL, if you had a fixed camera and it just has its own X, Y, and Z position, and it has its position in the world. Right, the OpenGL camera. But we have to create this sort of view matrix, this transformation, right? So the camera has a position, the camera has an orientation, and it's looking at, basically looking at a certain point in the scene or towards a certain, along a certain point in the scene here. So we can then use that transformation of that camera, the negative, like I mentioned, it's sort of doing the opposite. If the camera looks down, the other object sort of looks up, kind of thing. Right? And that's because the negative of the camera's rotation angles and the negative of the camera's location ultimately become this viewing transform that we can use to transform world points into points that make sense for that camera. All right. long story, the short story, or the short part of this long story is we have another matrix that we can apply to objects to make them appear that they are, at the positions that the camera would be seeing them from. It's kind of a little bit backwards, but or it feels may feel a little bit backwards, but it's not that backwards. So we call this model view matrix, which is a combination of the model's perspective or the model's location and orientation in the world and its transformation according to the view. So we create this thing called the MV, or the model view matrix, right? But there is another transformation necessary that's sometimes called the perspective or the projected transformation. And this has to do because cameras aren't necessarily 100% sort of linear, just straightforward things. They're not orthogonal, right? We have some projection and perspective in the camera. Right? What does that mean? What is projection or perspective? We can use a quick example of this here. That when you look at an image, right, you have a point of perspective, right? Things scale as they go in the distance. They become smaller in the distance. They become larger as they're in the front, right? So you have this perspective projection that is part of the viewing process. Okay. So what we're seeing now is this perspective view. And if you've used Unity, you may have checked, orthogonal camera versus a projected or perspective camera. This is ultimately now what we're talking about, right? Things are being scaled according to distance away from the camera, subject to perhaps distortions based on aspect ratios and cameras, and there's other things we can do to them. But the basic idea is this notion of a transformation based on a relationship to the camera that's more complex than just a location and an orientation. So the perspective view volume is also referred to the frustum. That's what the camera can see, the volume that the camera can see if you drew lines from the viewpoint to some far plane that describe the space. You have a near clipping plane and a far clipping plane, and then you have all of the objects that the camera can see within there, right? We talk about these clipping planes to say, well, okay, perhaps there's something as you get closer and closer to an object, you don't want it to be shown. You want it to be clipped. So things, the volume is what you can see. We can only see the things that are inside of this frustum. We're just define this. So we have this extra thing, this Z near plane and Z far plane for clipping. And the field of view is the relationship. This isn't necessarily a square here. The field of view, we might have a relationship between the width and height. Maybe it's square, maybe it's not square. There's this notion of aspect ratio because we have X and Y that could have some sort of relationship that makes sense. Let's look at the transformation and hopefully it'll make some sense. So we have here the perspective projection, or the projection matrix transform, which encapsulates our field of view, which is going to be our relationship between our X and Y in the volume. If you've seen a TV that is 16 by 9, you may have heard of aspect ratio, which basically says, okay, I'm looking at things that are 16 units wide by 9 units high. So that's the area that I'm interested in. So that volume is it's a non-square, it's a rectangular volume instead of just a purely square volume. We use that in here to affect the scaling. And then we have, the objects that are seen in the scene. We have our relationship of our near plane and our far plane. So we wind up with a perspective projection. Okay. And again, the good news is that largely once we establish these, we can combine them together. There is math. OpenGL will kind of do a little bit of this heavy lifting for us. And the easiest thing to do is for me to recommend that you actually, in your programs, you'll see this in Chapter 4 as you start to go with more complex programs. We'll talk more about Chapter 4's programs on Friday. We'll have things in there, and I encourage you, those who have already kind of caught up, you've done all the programs up through Chapter 2, which isn't an awful lot, and now kind of think about some of the math here. It's not really deep math. But you'll start to see it employed in the programs in Chapter 4. And to get a real sense of them, you can go in and change what the transformations are, and they'll change the orientation of the camera in the world, or changing the aspect ratio of the camera, or changing just the distance and so on. It becomes pretty straightforward to start playing around with those parameters within a real context. So if it seemed like we talked quick about these things, it's because we have an hour. So in order to look at something, we're going to build a look at matrix. We'll see, it'll go through this in the book. So ultimately, we're going to basically, this is a convenient matrix to say, okay, if we have a forward for a particular object, a side view for a particular object, an up view for a particular object, you may have seen forward, side, and up with regards to the kind of shorthand for things in Unity and Unreal. So you can go through the process and kind of create this shorthand look at matrix if you want as well. So we can kind of leave that as an open-ended practice here. We'll actually put these in place in the examples, in basically all the examples from here on forward. Okay. All right. So that got me to here with 4 minutes to spare. How's everybody doing? Did that, hopefully, things, especially if you've got the background already, certainly dot and cross products, it's a matter of using them. Does everyone feel comfortable jumping into Chapter 4? I'm not going to poll. You can just react to that. So the one thing, okay, I'm going to use this 5 minutes. Quaternions deserve at least, they deserve a lot more than 5 minutes, but I'm going to give them 5 minutes. Now, we talked about the Z, the issues or that we'd like. It'd be nice to be able to think of just X, Y, and Z rotations, Euler angles, and so on. But there's a special case. There's a number of different special cases that are problematic for Euler angles. And there is this concept, it's not just a concept, this problem called gimbal lock. And let me show you gimbal lock. Okay. Now, gimbal lock, if you're doing rotations strictly, purely as a set of X, Y, and Z that are combined together, ultimately, you can see here's a gimbal with 3 axes of rotation, right? So this is basically how we would think of this as an X. Normally we have an X, and then we have a Y, and then we have a Z that we do the rotations around. But in certain circumstances, these will align, and hopefully, yes. Okay, here we can see an example of what happens if you do a rotation by 90 degrees around the outer ones in this case, whichever they happen to be defined to, X and Y. What will happen is the inner one will align with the outer axis, right? So you can see here, this is the blue axis here. Early on, it rotates, and it goes into alignment because it rotated 90 degrees. It suddenly rotated and became aligned with the Z, right? So X and Z aligned with one another because of the rotation of Y. And as long as that Y 90-degree rotation is in place, the problem is you can no longer rotate in what would have been the X, right? X becomes a rotation in Z, right? But just because of the order things were done, and it kind of collapsed. You cause the axes to collapse on one another. And we'll leave that for a larger thing. You can read about that. But the solution is that instead of, there is a much deeper topic called quaternions. And what quaternions are, I'll give you the very, very simple version. And this is like if anybody asks, and you can provide this answer, you're reasonably well off. You say, okay, instead of defining a rotation as being an X rotation, a Y rotation, and a Z rotation, instead what you do is you define a vector. And you know how to define vectors. You can point vectors in any direction. We can say, all right, vector has an X and Y, Z, points in a certain direction. That becomes an axis. You say, okay, that is the axis. And then we have another value, a scalar, that just says, okay, rotate around that axis. And that's what a rotation is. Okay, so it's not a combination of an X and a Y and a Z in a rotation for each of those. Instead, we define a vector, and then we define a rotation around that vector. And that's sort of the nickel version of what sort of how a quaternion works. And the nice thing then is if you have that rotation and another rotation, remember we can interpolate between vectors and so on. So we can create these kind of deterministic interpolations between these rotations as well, right? And the nice thing is, thankfully, the math to convert from Euler angles to quaternions and back is relatively straightforward. The way that quaternions combine, so you can do multiple rotations, that's kind of a well-known solved problem as well. So, if you want to read a book or go on a multi-hour-long tour of quaternions, I'll post lots of examples, and we can talk more about those as things go on. But for now, just know about them and why we have this kind of jump back and forth between quaternions and Euler rotations. Quaternions wind up being very efficient and avoid issues like this gimbal lock problem. Okay, I'll post a lecture that kind of goes into some of the history about that. So consider that. We're not going to have to prove four-dimensional, doing three imaginary dimensions and four-dimensional math to get three-dimensional rotations. I'm not going to hold you responsible for that in this class. It's a great, fun topic, but okay. All right. So that concludes lecture for the day. So I'm going to stop the streaming, and basically now it's you should start digesting some of that math and go through the chapter in the book and look forward to chapter 4. And we'll kind of get there. And I'll start checking in with everybody as we go, and we'll kind of keep adjusting it'll be a sliding scale. Ultimately, everybody's responsible for all the material, but obviously we're going to have to sort of slide back and forth schedule-wise because of the whole remote operation here. We'll get it to work out. It'll work out. Trust me. Okay, any questions? Quick, post them to Discord. Otherwise, I'm just going to jump off. Otherwise, I'll be cutting into people's time. I'm already doing that.